Okay, so now that we have a good grasp of how to do stoichiometry in the strict sense in terms of just mole-to-mole ratios, but then also using masses, converting the masses to moles, and then using the mole-to-mole ratios, let's take a look at some other features now of, again, some more realistic examples of stoichiometry where we're going to encounter a couple of very important terms. So we're going to take a look, first of all, at two types of reactants that we will encounter in a chemical reaction. We're going to call them limiting reactants. These are also known as limiting reagents, which we'll abbreviate as LR. And then in contrast to limiting reagents, we have other things that are called excess reactants or excess reagents. And the name kind of suggests what these do or what their characteristics are. We'll take a look here at a very simple example to illustrate this point. Okay, so let's say that we are trying to make some sandwiches. Okay, and as I mentioned in a couple of the previous videos, a chemical reaction, chemical equation is kind of like a recipe. So we're going to follow a recipe to make our sandwiches. We're going to need 2 slices of bread. Okay, and just imagine that this is a slice of bread. And I need 1 slice of cheese. Okay, so this is my cheese. It's Swiss cheese. There's some holes in it. In order to make 1 sandwich. Okay, so we have we'll just write the word sandwich here. Okay, that is our recipe. In order to make 1 sandwich, we need 2 slices of bread, 1 slice of cheese. So we have it in essence a mole-to-mole ratio, right? 2 to 1 to 1. It's not obviously moles here. It's the number of slices of bread, number of slices of cheese, and the number of sandwiches that we get. So let's say I know how to make my sandwiches. This is the recipe I'm going to follow. Go to the pantry and I look and see what I have. I look in my fridge and what I have to work with are the following. So we're going to start with, I find that I have, let me rephrase this. If you have 16 slices of bread and let's say 5 slices of cheese, that's what you find in your kitchen. How many sandwiches can you make? Okay, it's a very basic sandwich. Yes, probably thinking to yourself is not anything fancy and doesn't need to be for our example. So how many sandwiches can you make? Just a cheese sandwich. Well, you can probably figure this out in your brain fairly quickly, but let's apply stoichiometry to this example. So what you want to do in a situation like this, we're going to do 2 sets of calculations. Okay, and we're going to start with each reactant separately. Okay, so let's say I start with the bread first. So I have my 16 slices of bread. Okay, so write that down. That's how much I actually have. Put that over 1. And then according to my ratio from this balanced equation or from this recipe, okay, 2 slices of bread are used to make 1 sandwich, right? So that's a ratio, and I can insert this here. I can say 2 slices of bread, put that on the bottom, because I want to figure out how many sandwiches I can make, are used to make 1 sandwich. Okay, slices of bread go away. Obviously now, if I just look at the slices of bread, I can make 8 sandwiches. But in order to make a sandwich, I need something else, right? You can't just make the sandwich out of bread. You also need the cheese. So if I do my second set of calculations now, and now I start with the cheese, so the 5 slices of cheese. So I have 5 slices of cheese. put that over 1. And then I want the relationship between the cheese and the sandwich. Well, here it is 1 slice of cheese to make 1 sandwich. That's a 1-to-1 mole ratio, if you will, or just a 1-to-1 ingredient ratio. So 1 slice of cheese goes on the bottom, or 1 sandwich goes on top. Okay, slice of cheese goes away. So if I just consider the slices of cheese, I could make 5 sandwiches. Okay, so I do 2 sets of calculations and I figure out how many sandwiches in this case I can make using the full amount of either of these. Now, realistically, if I have the 16 slices of bread and the 5 slices of cheese, I could really only make 5 sandwiches, right? So how do we figure that out? Well, because you need 1 slice of cheese and 2 slices of bread, and at some point, when you assemble your sandwiches, guess what you're going to run out of first? You're going to run out of the cheese. Okay, so the cheese then limits how many sandwiches can be made. In other words, it limits the product. It limits the amount of product that can be made. And guess what happens after we make those 5 sandwiches? Well, there's none of it left over. Okay, it's all used up. So what we say then in this example is our cheese is the limiting ingredient, but in this case, to use a proper terminology, it's the limiting reactant. Okay, it limits how much product can be produced, and it's completely used up in this reaction. Okay, so when I compare in my 2 sets of calculations, right, whichever reactant gives the smallest amount of product, that is your limiting reactant. And limiting reactant is LR. Okay, we're doing 2 sets of calculations because you have two ingredients or 2 reactants in this case. Well, what about the other reactant, the slices of bread? Well, the other reactant then we say is in excess. And you often see the word excess being abbreviated as X and S, the actual letters. So if the other reactant is in excess, that means there's some of it left over. And what's the other reactant in this case? The bread. And we can actually calculate how much bread is left over, right? So if we made 5 sandwiches and each sandwich required 2 slices of bread, then I used up 10 slices of bread, well, then there would be 6 slices left over at the end. Okay, so we have excess of that particular reactant. And that is going to be the same idea now when it comes to chemical reactions, right? We're not making sandwiches in the lab. We're performing chemical reactions, chemical changes, and it's the same idea. We're going to be provided with the amounts of each of the reactants. We're going to do 2 sets of calculations. Whichever one gives us the least amount of product, that is going to be the limiting reactant. The other reactant is going to be in excess, meaning there's going to be some of it left over. Application of this now in a chemical reaction. So here we're given a reaction we've seen before, an equation representing that reaction between hydrogen and oxygen to make water. And we see that it's already balanced. You always want to double check that your equation is balanced. And here we're told that 15 grams of hydrogen reacts with 15 grams of oxygen. It asks us which reactant is limiting, and then how much of the let's separate. That's A. B is how much of the excess reactant is left over. And then C, it says, what is the theoretical yield of water in grams? And we'll address that at the end. So let's take a look at the first part here. So it says, which reactant is limiting? Well, based on what we talked about before, we need to do two sets of calculations. We're going to start with each of the reactants. So I have my 15.00 grams of H2. I'm going to put that over 1. First step would be to convert it to moles. So for every 1 mole of H2, that's 2.02 grams of H2. That's my molar mass. Not H2O, but H2. Then I use my mole-to-mole ratio to get to the product, in this case, that I want to relate both of the reactants to. So according to my balanced equation, 2 moles of H2 produces 2 moles of H2O. So 2 moles of H2 produces 2 moles of H2O. Moles of H2 cancels. And then if I want to take this the last step, I can convert that to mass. So 1 mole of H2O. Molar mass of H2O is 18.02 grams of H2O. Okay, so we get the moles of the water cancel out. And then that's going to give us the grams of water, which we can then calculate. Okay, so this is going to give us 133.8 grams of H2O if all of the hydrogen reacted. We're going to do the same thing now with the oxygen. I'll do this in a different color. So we have the same amount, 15.00 grams of O2. Convert that to moles of O2 first. So for every 1 mole of O2, 16 times 2 is 32.00 grams. Grams go away. My mole-to-mole ratio now is 1 mole of O2 to 2 moles of the H2O. Okay, so 1 mole of O2 for every 2 moles. The H2O, moles of O2 go away, and then the last step, moles to grams. Same as the step above, 1 mole of H2 is 18.02. Grams of H2O, moles of H2O goes away. I can then calculate this using my calculator. It's going to give us 16.89 grams of H2O. So same thing as we did before, we're going to compare these two numbers. Which one is the smaller? Well, the 16.89 grams is the smaller. And how did I get that? Well, I get that from starting with the oxygen. So what this means then is that my O2 is a limiting reactant because it produces the least amount of product. It's going to be used up. There's none left over, which then suggests then that the H2 is going to be in excess. Okay, and that's the terminology that we use. How much is actually left over at the end? Well, we can work with our numbers here. We can use the 15 grams of oxygen because that's going to be the most important one now because that's our limiting reactant. We can now relate that to the hydrogen. Sorry, so 15 grams of O2. Convert that to moles. So 1 mole of O2, 32.00 grams. Our mole-to-mole ratio from the balanced equation says that there's a 2-to-1 mole ratio between the H2 and the O2. Okay, so 1 mole of oxygen requires 2 moles of hydrogen. We can convert that then to mass. So 1 mole of hydrogen is 2.02 grams of H2. Okay, so now we are relating the oxygen, the limiting reactant, to the one that is in excess. So if we evaluate this, we are going to see that we need 1.875 grams of H2. Okay, that's needed to react with all of the oxygen that we have. Now we started with 15.00 grams of H2, and if we're going to use up 1.875 grams, we just subtract that, right? So 15 minus 1.875. This is how much is used up in the reaction. We can then determine how much of the hydrogen is left over. So this is going to give what? Get 5, that's 2. It's 1, and then this is 13.125 grams of H2 that is left over at the end, right? This is in excess. Just like in the example we did above, we'll have a bunch of the slices of bread left over, right? We determined there were 6 slices left over. Same thing here. Our reagent that is in excess, there's some of that that's going to be left over. We're going to use the limiting reactant to determine how much of the other reactant is needed, subtract that from how much of that reactant we started with, and that gives us the excess, the amount of that reactant left over. So the other thing to keep in mind here now is once we determine what our limiting reactant is, that limiting reactant actually determines this characteristic, the theoretical yield. Okay, and that's a very important thing to note. So the limiting reactant, so the LR determines what's known as the theoretical yield for that reaction. And the theoretical yield, which you often abbreviate as TY, this is how much product can theoretically be made if everything worked out perfectly. Okay, and that's determined by the limiting reactant, whatever that reactant is. Now, in some cases, so we can actually do this, we can calculate this. We can calculate the theoretical yield from stoichiometry. We can also perform the reaction. We can actually do this in the lab, and we can measure the amount of product that we get. And when we perform the reaction and we measure the amount of product that we obtain, that amount is called the experimental yield. And that's a different term. So experimental, sometimes it's called the actual yield, is how much product is obtained from actually carrying out the experiment. Okay, so we have 2 types of yields. Theoretical yield we get from the limiting reactant from doing the stoichiometry. We have experimental or actual yield we get from doing the experiment and measuring the amount of product that we get. And we can compare those 2 values. The way that we compare the theoretical yield, what we predict we should get from the experiment, to the experimental yield, which we actually get from the experiment, is we can calculate something known as the percent yield. The percent yield is a very simple formula. Okay, it's the actual yield, actual or experimental, divided by the theoretical yield. And then as a percentage, we times it by 100 to get the percentage. So really what it is it's going to tell you how good you are at getting to a value that you are supposed to get, right? The theoretical yield is if everything worked out perfectly, that's how much you should get. Well, when you actually do the experiment, you're going to get a certain amount, and you can compare them to see how good your or to gauge how good your technique was, how good you actually did the experiment. All right. So very simple relationship, but there's a lot of stoichiometry that goes on, for instance, to determine your theoretical yield from using the limiting reactant in a particular equation.